Hello, and welcome to my final project presentation. This is the class EGR 214 Numerical Methods for Engineers in the fall 2024 semester at Cape Fear Community College. My instructor is Dr. Hans Chapman, and my name is Keenan Kraus. This presentation is how to go from Cartesian equations to polar equations in both Matlab and Python. When graphing a circle, it requires quadratic terms in Cartesian form, but putting a circle in polar coordinates simplifies this. By converting to polar form, you're working in the coordinate system that aligns with the geometry of the problem, making graphs and relationships more intuitive. When combining polar and Cartesian coordinates on the same plane, we align their origins and place the initial polar ray along the positive x-axis. The ray, where theta equals 2 pi and r is greater than 0, corresponds to the positive y-axis as shown in the graph. The two coordinate systems are connected by the following relationships: x equals r cosine theta and y equals r sine theta. The first two of these equations uniquely determine the Cartesian coordinates x and y given the polar coordinates r and theta. On the other hand, if x and y are given, the third equation gives two possible choices for r, a positive and a negative value. For each x and y both cannot equal 0, there is a unique theta satisfying the first two equations, each then giving a polar coordinate representation of the Cartesian point xy. Imagine we start with a circle defined by the equation x squared plus y minus 3 squared equals 9. This circle is centered at 0, 3, and has a radius of 3. Our goal is to rewrite this equation in terms of polar coordinates r and theta. First, we expand the term y minus 3 squared, which gives us x squared plus y squared minus 6y plus 9 equals 9. When simplifying, the constant terms cancel out, leaving us with x squared plus y squared minus 6y equals 0. Next, we introduce our polar substitutions: x equals r cosine theta and y equals r sine theta. Then you factor out r, and that gives you your two solutions: r equals 0, which is the origin, and r equals 6 sine theta. Now we have our Matlab numerical solution for this problem. First, we start with our sims x, y, r, and theta. Next, we can define our equation with the variable Cartesian EQ equals x squared plus y minus 3 squared equals 9. Next, we define our polar coordinate transformations, which is x polar equals r times cosine theta and y polar equals r times sine theta. We then substitute x and y in the equation with the polar forms, which is polar EQ equals subs Cartesian EQ, and then our xy, and then our x polar, and then our y polar. We then simplify the polar equation by giving the variable polar EQ simplified and then using the simplify command to simplify our variable polar EQ. Next, we then solve for r, where we define it as r underscore EQ and then to equal that to solve command followed by our polar EQ simplified variable and r. Lastly, we display the final polar equation with the display command, which gives us our solution of 6 sine theta. For our Python numerical solution, our first step is we import SymPy library, which is a symbolic math library in Python. It allows us to find variables, manipulate equations, and solve them algebraically. Our second step is to define symbolic variables. We define our 4 symbolic variables as x and y represent the Cartesian coordinates, and r and theta represent the polar coordinates. These variables will be used to define the Cartesian equation and perform substitutions. Our third step is to define the Cartesian equation. The Cartesian equation of the circle is x squared plus y minus 3 squared equals 9. We use sp.eq to define this equation in symbolic form. Our fourth step is to define the polar transformations. The relationship between Cartesian and polar coordinates are x equals r cosine theta and y equals r sine theta. Our step 5 is to substitute polar variables into the Cartesian equation. We substitute x and y with r cosine theta and r sine theta respectively into the Cartesian equation. This transforms the equation from Cartesian to polar form. Our sixth step is to simplify the polar equation. The substituted equation is often more complex than needed. The simplify function reduces it to a simpler equivalent form. Then our step 7 is to solve for r, where we solve the simplified polar equation for r, isolating the radial distance as a function of theta. Then we solve the function, it returns all the solutions. For step 8, we display the final polar equation. We print the solutions for r. The polar equation of the circle will appear as r equals 6 sine theta. Then thank you for watching.